This will work. All right, good afternoon, everyone. It's a pleasure to introduce Michael Johnson. So Michael's an astrophysicist at the Harvard Smithsonian Center for Astrophysics. He got his PhD from UC Santa Barbara in 2013 and has been at Harvard ever since. He's one of the inaugural members of the Black Hole Initiative. You can see it there. Michael studies galactic and extragalactic black holes and pulsars with radio astronomy, especially focusing on imaging techniques at very high angular resolution. He developed many of the image processing techniques that make movies of rapidly evolving black holes, and has worked on how to study the magnetic fields of black holes with polarimetry. He led was one of the leaders of the imaging team that made the famous pictures of the donuts that we all know and love. And then about a year ago, Michael got the New Horizons Prize in Physics, the New Horizons in Physics Breakthrough Prize for his work on photon rings, which I think we'll hear more about today. So look forward to a exciting talk from Michael. Thanks.
Thanks so much. Well, thank you so much for the invitation to visit. It has really been such a treat to spend the day here and see a bunch of old friends and just hear about so many of the incredible projects that are going on. You know, in the US, Caltech really stands out as one of the anchors for the radio community going back many decades. And so it's just a lot of fun to be able to connect these new projects with things that really were born here and that are being continued. So I work on broadly radio interferometry. This is the same technique that underscores things like DSA 2000 and many of the other exciting facilities in astronomy. But the way that I've been using it most recently is with very long baseline interferometry to achieve the sharpest resolution across any astronomical technique. And we use that in particular to study black holes. So I just want to tell you a little bit about where we're at today and hopefully where we're going to be going over the next decade. To set the stage, I just love this movie you may have seen. It's a zoom in of the M87 galaxy. And the wonderful thing about this is that every image that you're going to see in this is actually a real astronomical observation. So it's zooming in, and it starts off with the X-ray and optical images of M87, where all you can really see is this fuzzy ball of stars with just the hints of a jet extending away from it. And using radio interferometry, we can go deeper into the source, and there the jet completely takes over the image. And as you look at higher and higher frequencies, the jet becomes more and more translucent until you get to 230 gigahertz. And this is the first ever picture of a black hole taken by the Event Horizon Telescope and released in 2019. So this is probably very familiar to you. It's this glowing gas near the black hole, heated to about 100 billion degrees, and it's emitting synchrotron radiation. It's brighter on the bottom than the top because this is gas that's in relativistic motion around the black hole. So there's relativistic Doppler effects that make it brighter when the gas is moving towards us and fainter when the gas is moving away from us. And there are kind of two incredible scales to grapple with in this image. One is just how big this black hole is. And you can get that from just putting a ruler on the image. The black hole is trapping the light that comes too close to it. And so it leads to this dark central region. And that tells us that the black hole is about 6 billion times the mass of the sun. One of the most massive black holes studied by any method in astronomy, and one of the biggest ones in the universe. But the other extraordinary scale to grapple with is just how small this is on the sky. So it's a large black hole, but the event horizon of a black hole is very small. If you made the Earth into a black hole, it would be about an inch across. You could hold it on your finger. Neutron stars and stellar mass black holes are kilometers in size. And so even though this is such a large black hole, it's a very small angular size on the sky, about the same size as an atom held at arm's length. So the difficulty in really getting these images is coming up with techniques that can probe such fine angular scales. So the other primary target for the Event Horizon Telescope is Sagittarius A star. the black hole at the center of the Milky Way. And it's particularly famous because it's been studied for decades in the infrared, where you can see these orbiting stars on Keplerian orbits, or very close to Keplerian orbits, with the shortest period of 12 years here. So they're getting whipped around by this unseen object right at the heart of our galaxy. And they're able to measure that black hole's properties extremely precisely. So they make a prediction that there should be a black hole with 4 million times the mass of the sun sitting right there at the center. But a couple of things here to keep in mind. One is that the gravitational field experienced by these stars is actually fairly weak. So the strongest gravitational acceleration experienced by any of them at their closest approach is actually less than the gravitational experience that we have here on the Earth. So the closest that they get is about 1,000 times the Schwarzschild radius of the black hole. So it's just the really gentle regime of the black hole's gravity. So this is a natural target for us to look deeper and see whether or not there's a black hole there. But when we do that, it turns out that there's another effect that we have to contend with, and that's actually interstellar scattering in the diffuse ionized interstellar medium. So Sag star was discovered in 1974, and within 2 years, observers realized that they were actually not looking at some resolved source studying black hole emission, but they were actually seeing just a scatter-broadened blob on the sky. And the reason they knew that is that it's a very steep frequency dependence in their measurements. So as you look at longer and longer wavelengths, the source size is growing with the squared observing wavelength. This is a very generic property that just results from the plasma dispersion relation in the interstellar medium. So these are all actual measurements of Sag star. So the good news is that this is kind of unique to Sag star. The scattering here is about 1,000 times stronger than M87 and other lines of sight that are off the galactic plane. So we don't have to worry about it for most sources we look at, but it does kind of block our view of the center of the galaxy. And it's like looking through frosted glass. It smears out all the small scale structure. But if you look down here at this is just showing the source size as a function of the observing wavelength, you can see at these low frequency, or at the very high frequencies, it's breaking away from that lambda squared behavior. And so what's going on there is that the intrinsic source size is actually contributing. You're getting to a regime where the thing you're seeing on the sky isn't just dominated by the scattering. So the fact that the intrinsic source there is poking out is telling us that those are the frequencies that we need to be able to start to study the intrinsic structure here. And just to give you a sense of this is a simulated image where I've just taken a black hole image and scattered it at 400 gigahertz, where you can see that it gets a little bit of a fuzzy glow on it. And what I'm going to do is I'm just going to turn that frequency down. So we dial it down, you can see the scattering kicks in, and then it becomes kind of catastrophic once we get to 85 gigahertz. And that frequency is selected because that's the highest frequency observations of Sag star ever made using VLBI before the EHT. So this is why the EHT was such a big step forward for Sag star, because even if you had a perfect image on the sky, a perfect instrument at that frequency, the scattering is blocking your view. So we pushed to 230 gigahertz where we have a much sharper view. So we have these stellar orbits near Sag star. They tell us that there should be a black hole with 4 million times the mass of the sun. Einstein's theory of relativity then tells us what that should look like, and that the black hole should cast a shadow with a particular diameter. So this annulus is showing the range of possible shadow diameters from Sag star. And the thickness there is the uncertainty. That's actually not because of uncertainty in the stellar measurements, which are exquisite. That uncertainty is because we don't know whether or not the black hole is spinning. And the spinning black hole, the frame dragging affects the size of the shadow. It makes it a little bit smaller. So we can compare that with the first EHT image that was released a couple of years ago, and it's in perfect agreement. So this is just really a triumph of a theoretical prediction for what black holes should look like from 100 years ago, matched to these decades of infrared observations of stars, and then finally confirmed using this technique of radio interferometry. So one lesson from all of this is that it's very hard to make images of black holes, but the reason is not because black holes are black. It's because they're incredibly small. And so the technique that's finally bringing them into view is this technique of very long baseline interferometry. And it's a fairly technical topic, but I wanted to give you just a little bit of intuition about how this works. And to understand that, we can draw some inspiration from ducks. So here's some ducks. They run and they jump into this pond and they start kicking their feet furiously. And so as they're doing that, they're stirring up the water near them, and they're doing it in a turbulent and irregular way. But the interesting thing is that if you look far away from where those ducks are, it's not turbulent and irregular. It's actually these nice, coherent, outward propagating wavefronts. So again, close to the ducks, it's turbulent and irregular. Far away, it's nice, coherent wavefronts. So the thing that I want you to imagine is suppose that you're standing on the boundary of this pond, and the game is that you have to tell me where the ducks are in the pond. We'll say that the game is that you're blindfolded, you can't see them, and you also can't hear them. So all you can do is you can wade right into the edge of the water, and you can feel the water lapping against your feet as you're standing there. And my question for you is, can you tell me where the ducks are in the pond just from that pattern of the water lapping against your feet? Okay, so let's break this down a little bit more. We'll do our toy problem. So on the left, we have some ducks that are very close together in the pond. And on the right, we have ducks that are spread out far apart. So let's start with the one where they're close together. We're going to let them start kicking their feet. They're stirring up the water. It's becoming turbulent and irregular. And then further away, you can see that nice, coherent, outward propagating wavefront. And again, you're going to imagine that you're standing right here, and you just feel the water going up and down against your feet. So pretty straightforward. So we'll do this now again for the ones on the right, the ducks that are a little. So we let them start kicking their feet, stir up the water, turbulent and irregular. And then again, just imagine that you're standing there on the boundary, feeling the water lapping against your feet. So in these two cases, there are a few things to notice. One thing that you can measure is the amplitude of that sloshing pattern against your feet. And it turns out that in these two cases, that amplitude is identical. That tells you how many ducks there are, but it doesn't tell you where in the pond they are. It carries no information whatsoever about that. But the second thing that you can measure would be the coherence length. So let's say that you're not there by yourself, but you have a friend, and they're also standing on the edge of the pond, and you're able to compare the two patterns that you see. In the case where the ducks are close together, you and your friend can be very far apart, and you'll be seeing the same patterns. Whereas in the case where the ducks are spread out, you and your friend have to be very close together before you start to see different lapping patterns against your feet. Okay, so this is all pretty whimsical, and it may not seem like it has much to do with radio interferometry, but they turn out to be mathematically identical. So in our case, we don't have ducks, but we do have electrons. And the electrons are gyrating around magnetic fields. They're sending out ripples of electromagnetic waves that then propagate towards us. And we're not going to be standing on the edge of the pond, but what we do is we take these telescopes and we spread them out as far as we can. And then we compare the electric waves that are received at each pair of telescopes. Any one telescope doesn't tell us anything except how many ducks there are in the pond and total flux of the source. But the comparison between each pair of telescope actually encodes that information about the distribution of ducks in the pond, or in this case, the image on the sky. And it turns out that there's a very elegant correspondence between the correlations that are formed by every pair of telescopes and that image, which is just a direct Fourier transform. This was originally discovered by Michelson, but it's known as the Van Sittert-Zernike theorem. And this was developed by Martin Ryle, who got the Nobel Prize in 1974 for developing it as a technique. So it's this really beautiful thing that in radio interferometry, all we care about is pairs of telescopes where the distance that we spread them apart is sampling different spatial information on the sky. Telescopes that are far apart sample very small scale features. Telescopes that are close together sample large scale features. And by piecing all of that information together, if you can sample the whole range of telescope distances, then you can just invert this Fourier transform and turn your measurements into an image. So that is the basics of this technique that is how the Event Horizon Telescope works. It's not one telescope, but this collection of telescopes all over the world. And the wonderful thing is that none of these telescopes was actually created to do interferometry in this way. So it's a very sort of agnostic technique where you can pull together a very heterogeneous array and use it to do profound science. So the two things that we had to do with each telescope is we had to add very high precision clocks. So we typically use active hydrogen masers at every site. And that's because the signals have to be perfectly synchronized. Like you and your friend, if you're going to look at these splashing ducks, you can't go one day and have your friend go the next day. It has to be measurements at the same time to measure that correlation of the signal. And the other thing that we have to install is very high-speed recording equipment. And that's because the signal that we're looking for is extremely weak. There are all these fun analogies in radio astronomy for this, but here's one. And that's that if every telescope here pointed at M87 for a year and recorded continuously, the total amount of energy received from M87 would be about the same as when you pop a small soap bubble. So it's an unthinkably small amount of energy. And what we do is we turn these telescopes basically into really large digital light buckets. So we sample, we're swallowing as much of the light as we can. We're recording very wide bandwidths at every site. And so the EHT is kind of famous for shipping around literally truckloads of hard drives, which are just filled with the raw data that's needed to do these correlations and detect the signal. So that's kind of the nuts and bolts of how the EHT works. But the real question is, what does it mean? What does this orange donut actually tell us about astrophysics? And in the EHT, the gold standard for the interpretation of our images is these three-dimensional general relativistic magnetohydrodynamic simulations. So here's one example. This is a full three-dimensional flow of accreting plasma near a black hole in a curved spacetime. And to put this in context, 1 second in this movie corresponds to about 1 hour of observations of Sagittarius star, or a couple months of observations of M87. So one neat thing about looking at such small angular scales on the sky is that you actually see things evolving in real time. And these are scales where we can stitch together observations and actually watch accreting material or ejected material on event horizon scales. So what we do is we build large libraries of these simulations where we tune the plasma parameters to different values, and we can also look at high spinning and low spinning black holes and start to explore how that changes the image and what it means to look at the EHT image for the astrophysics and the fundamental physics of the black holes. And here it turns out that our constraints are remarkably weak. So it's just one example. Here's a simulated image. It's a so-called MAD image, which stands for magnetically arrested disk. So this black hole has swallowed enough magnetic flux that it actually is dynamically dominant, and it can freeze the inflow of additional material. The A star there is the spin of the black hole. So this is nearly maximally spinning, close to a fundamental limit for how fast black holes can spin. And R high is just a phenomenological plasma heating parameter that's set to 10 here. Okay, here's another example. This is a so-called sane model. This is one that instead has very weak magnetic fields, so they become turbulent. The black hole here is not spinning, and the electron heating parameter is the same as in that other simulation. And then finally, here's another one. This is also a weakly magnetized black hole. Now it's nearly maximally spinning, but it's got a minus sign on it, which means that it's a retrograde accretion flow. The black hole is accreting one way, and the accreting material that's falling onto the black hole is actually rotating the opposite direction. And we've changed this electron heating parameter in this case. And the incredible thing is that when you blur these to the resolution of the EHT, they are all compatible with our image. So we've taken these wildly different parameters for both the physics of the black hole and also just the properties of the accreting material. And we can tune both of them substantially and still be consistent with the EHT. So one of the big surprises for us in the EHT was just how resilient these simulations were. It's like the entire simulation library seemed to be consistent with the EHT image. But what was interesting is that when we looked at Sagittarius star, we saw the opposite. So this is a similar thing, but since these results were later, we had larger simulation libraries. So every cell here is a different simulation. These take weeks to run on a supercomputer. It's an enormous amount of work to generate all of these simulations. And here you can see there's MAD simulations on the bottom, SANE on the top. The different angles of the wedge or the different viewing inclinations of the black hole, because we don't know what angle we're looking at the spin axis of Sagittarius star. It's also tuning the strength of the spin, and it's looking at both these prograde and retrograde models. And this is now looking at just a series of constraints based on the EHT data and examining which of the models are able to pass those constraints and which ones are rejected. So you can see that there's actually only 2 green boxes here. There are only 2 models in this entire set that are consistent with the full set of EHT constraints. But the catch is that this has ignored one of the constraints, which is the overall variability of the system. So just looking at the light curve, the total flux is a function of time. And when we add that additional constraint, none of these models is compatible with all of our measurements. So what we're seeing is that we have this incredible tool, right? These general relativistic magnetohydrodynamic simulations that helps us interpret our observations, but we're seeing cracks in the foundation. In some cases, they seem to be too permissive. In other cases, all our models are ruled out. And what we need is really new observations that are going to drive rigid constraints that aren't so model dependent. One interesting feature in the EHT over the last few decades is that as we take better and better data, our constraints get weaker and weaker. And this is that we're learning more about the physics of these systems, and we're learning more about the things that we just simply don't know. So the question is, how can we improve the resolution of the EHT? How can we get better images? And for that, we can take some inspiration from Charles Darwin. So not Charles Darwin, the naturalist, but actually his grandson, who was a physicist. And so Darwin was looking at this problem of, supposing you have a star located near a black hole, how would that appear to a distant observer? So what Darwin realized is that there would be an image of this star, and it would be distorted by the curved geodesic by the lensing of the black hole's space-time. But he realized that wouldn't be the only thing you saw. So he wrote, each star, in addition to its direct image, will show a series of faint ghosts on both sides of the black hole. There will be a ghost on its left, just outside 3√3m. Furthermore, there will be secondary ghosts on both sides, still closer to 3√3m, which come from rays that have gone a complete circle around the black hole before escaping to the telescope. The successive ghosts of a sequence crowd together more and more closely to such an extent as exactly to counterbalance their increasing feebleness. Then he added, this result seems to have no practical importance at all. So it turns out Darwin was right about all of this, except the last sentence. So here's the EHT image, and we think that if we could see with perfect angular resolution, we would see something that looks more like this image, which is simulated. And it turns out that every simulated image from GRMHD of a black hole has this sharp feature called the photon ring. So the photon ring is not one ring, it's actually a stack of increasingly sharp subrings. And these are indexed by the number of times that light went around the black hole before escaping to reach us. And so because the subrings are produced from light that spent a lot of time in this strong gravitational well, they're very sensitive to the black hole's properties, and they have self-similar relationships because they're all produced from the same emitting material. So just to give you a sense of this, here's a movie that just shows you the passage of light as it comes near a black hole before it escapes to a distant observer. So for the EHT, most of the light we see comes from rays that are fairly weakly lensed by the black hole, and it produces this rather diffuse image. But if you aim the light rays just right, it turns out that they can make U-turns around the black hole before escaping. And the wonderful thing about GR is that those looping photons, they pile up on this thin ring feature called the photon ring. And then if you aim them even more precisely, you can get it to go around the front and then the back and the front again. You can get it to take more and more loops. And every time it takes more and more loops, it becomes exponentially demagnified into a sharper and sharper ring image. And so the full image that we see from a black hole is the sum of all of these, which is why this photon ring is universal and why it appears on all black hole images. It's created by the black hole spacetime. So just as one example of this is now, again, one of those GRMHD simulations. It's not a toy model or something. This is the actual three-dimensional computer simulation. And on the right is just a few cross sections through that image in the horizontal and in the vertical direction. And you can see that it has this peculiar structure where there are these humps, and then they'll have a sharper one, and then a sharper one, and so forth. And that's each of the successive photon rings stacking on top of the previous image. So thus far, this is kind of just a curious academic feature. It doesn't really seem to have much to do with observations. But it turns out that photon rings are perfect to study using interferometry. So here is the actual interferometric response of this image. So this is you and your friends standing on the edge of the pond. The x-axis is how far apart you are. So as you move apart, you'll find that you're seeing a less and less correlated signal. The y-axis here is just the correlation. But the weird thing about these ring images is that you'll see that your correlation will decrease as you're moving apart, and then it'll start to increase and decrease and increase, and that's what's encoding all of the source properties. So on these short baselines that we can access from the Earth out to about 10,000 kilometers, it's a pretty complicated signal because it's folding in all of the diffuse emission and structure in the accretion disk in the jet. But if you go to long baselines, all of that complexity fades away, and you're left with just a very simple damped periodic oscillation. And the reason for that is that's where the photon ring is taking over. And this periodicity here is telling you the diameter of the photon ring along the direction of the baseline. So here there's red and a blue curve. That's just baselines that are horizontal or baselines that are vertical. So I can't express enough how weird this is. Interferometry, we're sampling the Fourier transform, which is a global thing. Usually knowing some little patch of Fourier space tells you nothing about the image. That's why we need filled UV coverage and lots of telescopes. But here, you can imagine just marching out to long baselines and just reading off a little bit of the range here and measuring the periodicity, and that's telling you the photon ring properties. And it's a very special property of looking at these sharp rings on the image that are produced by the black hole. We've never studied sources in astronomy that produce this kind of signal. We only need a little bit of the information to get exactly what you're after. And it's even more than that. So the interferometer is already filtered so that the long baselines are just seeing the photon ring for you. That's what you want. But also, if you look at the red and the blue curves here, you'll see that the peaks are drifting with respect to each other. And that's because the horizontal and vertical directions have slightly different diameters. So it's actually telling you that this is not a perfect circle. Your eyes can't pick that out in the image, but the interferometer sees it right away. And the reason for that is because frame dragging is introducing a little bit of asymmetry in the photon ring. So this is just showing you the expected asymptotic photon ring for a non-spinning black hole is a perfect circle no matter what direction you look. But if you let the black hole start spinning, then what happens is that the shadow in the photon ring becomes displaced and they get compressed in the direction orthogonal to the black hole spin. So by an interferometer and sampling all these different angles, you can very precisely measure the shape of the photon ring, and the non-circularity encodes that information about whether or not the black hole is spinning. So this gives us a really clean way to measure black hole spin directly for the first time. So I also just want to give you a little bit of the flavor of the mathematics behind the photon ring. It's just a really wonderful object in GR. So for this, here the sphere is representing the outer event horizon of a black hole. And I'm going to show you the passage of light that's trapped on circular orbits near a black hole. So for a non-spinning black hole, you can put that at just the right distance, and then it can orbit in any direction you want. It can go prograde or retrograde. And you can tilt the orbital plane because it's all symmetric. And this together forms the photon sphere, something that's very familiar. But if you let the black hole start rotating, the black hole sphere actually becomes a black hole photon shell. And this is something that's actually quite peculiar. So photons that are rotating prograde have to move inward. They kiss the event horizon. And the retrograde ones have to move outward to counteract that frame dragging. You can also shoot them off the equatorial plane. So now we can have them go over the pole. But as they're moving over the pole, they're getting pulled by the frame dragging. And so they trace these very intricate structures. And it turns out that this orange guy that's going over the pole is actually still living on a sphere. So you can shoot these photons off the equatorial plane at any angle you like, but at any angle you want to shoot, there's only one particular radius where the photons can actually live on a spherical surface and orbit the black hole. And so together, this is what composes this feature of the black hole's photon shell. Now, the reason this is important for imaging is that these are unstable orbits. So if you just imagine nudging the photons just a little bit, one of two things will happen. If you push them a little bit towards the black hole, they'll quickly fall in and be trapped forever. And if you push them just a little bit away from the black hole, they'll escape to infinity. And so they're the ones that actually form the photon ring. But what's wonderful about the photon ring is that as you look around your image, it's actually different angles on the image are tracing out different emission radii near the black hole. So it's actually this beautiful holographic mapping where you can actually do tomography and different emission radii by probing around the edge of the black hole's photon ring at different angles. And so those guys on the left are the ones that came in and kissed the event horizon. So it's this wonderful feature. This was originally studied actually by Jim Bardeen, who wrote, it's conceptually interesting, if not astrophysically very important to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. So I love these theorists who are so candid with the limitations. Okay, so now we know that there are photon rings in black hole images. We know that they have the imprint of the black hole spacetime in a very special way. And the question is, what do we need to go measure them? And for that, it turns out there's some critical technology that happens to be just emerging now. So one of the important things is the recording bandwidth. So for the Event Horizon Telescope, we had to record, again, these truckloads of hard drives. To put this in context, RadioAstron is the most recent mission that did space very long baseline interferometry. And it streamed down data at 128 megabits per second. For the EHT to make its first detections required data at 4 gigabits per second. In 2017, when we made the first images, it required 32 gigabits per second, and our current data rates are 64 gigabits per second. In going to space, there's less signal there, so you need even higher data rates to get the same sensitivity. So our target to do the Black Hole Explorer and to make this interferometer in space is actually 64 gigabits per second. And the extraordinary thing is that that's actually possible using laser communications. So over the past decade or so, there's been a series of really incredibly exciting Pathfinder experiments, starting off with laser communications transmitting data all the way from the moon to the most recent projects like Psyche, which was just launched a few months ago, and maybe you saw in the news about streaming HD cat videos from deep space. But the particular mission that's exciting for us is this one called T-Bird. So T-Bird is a CubeSat. It's got a 1 watt laser with about a 1-inch transmission aperture. And it was downlinking data at 200 gigabits per second with this incredibly small, low-profile satellite. You can hold the whole system in your hand. It's a few kilograms. And it just deorbited last month. So this is telling us that the laser communication at these extremely high data rates is possible now. That's 1,000 times faster than Starlink, 1,000 times faster than the internet at your house. And this is something that can be done on a CubeSat now. So what we're doing with the Black Hole Explorer is we're trying to bring in this new technology to be able to link with these extremely sensitive ground telescopes to get enough sensitivity to detect a photon ring. So we've created a mission that has an antenna that's 3.5 meters. It'll do simultaneous dual band observations. The low band is about 100 gigahertz, and the upper observing band is at 300 gigahertz. The reason for this is that all of our phase errors are non-dispersive, so the low band is sort of like a calibration band. It tracks fluctuations from imperfect clocks and from imperfect knowledge of distance, and can then apply those to the high band to do long coherent integrations. It'll sample 48 gigahertz of analog bandwidth with a total data rate of 64 gigabits per second. And it's going to orbit at an altitude of about 20,000 kilometers. So this is a 2-year mission. It's a very focused experiment. I think the most exciting science will all happen in the first 2 months of the mission. And it's relying on this extremely high data rate using laser communications. So with those parameters, we can simulate the kind of data that we would get with this mission when linked with existing EHT telescopes. So here the gray points are the ground baselines, and the colored points are the ones that we would get with BHEX, where you can see this clear ringing signal from the photon ring. We can also turn those into images, and these are examples of showing with the simulated data the kind of images that we get with just the ground versus the ground plus space. And then we can also use new techniques that I'll talk about in a moment to try to make measurements of the black hole space-time parameters. And this is just showing simulated data when we're trying to get posteriors on the mass and spin. And so for the mass, this would resolve discrepancies even among recent measurements over the past few years. But the really exciting one is that this would be the first ever measurement of the spin of M87. So overall, BHEX would be a worldwide hybrid observatory. All the red dots here are the ground radio telescopes, and the stars are potential optical terminals to do the downlinking of the data. And here on the right, this is the baseline coverage. In interferometry, we always call it UV coverage. But the kind of amazing thing here is that the red points fill in the center well, and then the space baselines are actually sampling the UV coverage very nicely. So it's fairly filled UV coverage. What that means is we're not just looking at some little slice on lines and measuring a periodicity. We can actually make images quite well. So this is just one example where we've taken a simulation and we've done synthetic observations twice a week for 3 months. And so you can see those together and we can actually study not just images of black holes, but movies. So this is the kind of thing that we would get with the current EHT. And this is what we'd be able to get once we add the space baseline to it. So you're able to start to see these threads of plasma that are getting pulled around the black hole. And then the averaged image, every sharp feature you see here is an interpretable gravitational signature. So this very dark region right in here, we call the inner shadow. That's actually rays where you trace them back from your eyes, and they land on the black hole before they cross the accretion disk. And then outside that is this photon ring that's very sensitive to the black hole's mass and spin. And I think something that I'm really excited about this is that the algorithms to do this sort of analysis don't exist yet. So BHEX is a computational telescope, like all interferometers. We can point it act in computers on the ground. This is 3 of the students who actually made this simulation. They're up at 2 a.m. at a conference in Vanderbilt, trying to create new techniques that are capable of doing this. But the only thing I know right now is that the algorithms to analyze these data just don't exist right now. And it's this wonderful challenge for us. And I guess I wanted to walk you through just a little bit of where we're at today and why this is such a nice problem for us. In 2014, many of you may remember seeing the first time ALMA released an image of HL Tau, this beautiful image of a protoplanetary disk. And it's not just the image that's impressive in the instrument, but also they released these as Python scripts. It's reproducible, you can run it yourself, and that's actually not the case for standard radio imaging techniques before this that are very user intensive. In 2019, we released the first EHT image of M87. Katie was a huge part of this, and I think it was such a fun process, partially because we felt like we were really disrupting the norm. It's not just that we were doing scripts that are reproducible. We were also looking at uncertainties in the image. So this is tuning across thousands of different parameter combinations of the image to try to understand, how do different imaging choices affect different imaging features. So we published things like our mean image, but also the standard deviation. This felt, can I use the word disruptive? But it really felt novel and fresh, and I think we were really proud of this work. And it's incredible that this is so obsolete now, and to go from something that felt so fresh only 5 years ago to algorithms that have made all of this obsolete in only 5 years, I think is really exciting. So in 2022, we released the first images of Sagittarius star. This again had multiple imaging methods, but we started looking at formal posterior explorations using modern samplers and a lot of modern statistical machinery that's quite exciting. And so here, you also have to keep in mind that the image is only the first step here. We want to get at the physics of the black hole space-time. So for the EHT, we usually go from the image, we then do feature extraction, we then do these pass-fail tables with GRMHD. We try to get those to physical constraints. It's this fairly tortured process. And what we really want is formal posteriors on the parameters of interest from the black hole, things like the mass and spin. We don't want to have all these different steps that each have their own uncertainties. And so one thing that we've been doing is developing new techniques that actually look directly at the black hole properties of interest, instead of trying to do that after the fact, using the images as input. So just as one example, one technique that's been developed as a lot is to try to fit sharp rings directly to the EHT images. This is really exciting. We might be able to lock onto the photon rings directly with our existing data. And so this technique of hybrid imaging was developed. It's able to lock onto this sharp image, measure it very precisely, and do some interesting science with it. But the problem is when we try this on simulated data, we can repeat the test, but for a simulated image that doesn't have a photon ring, and it still finds one. So this is a fully Bayesian method, and yet we're finding that these methods have a lot of subtleties to them. They produce false positives, they have subtle biases, and a lot of work is needed. So another thing that we've started looking at is instead of trying to do this geometric analysis just with the image on the sky, you say, let's just go straight to the black hole spacetime itself. Let's model in the basis of the emitting material near the black hole. And I got really excited about this when we first started looking at polarized images of the EHT. So this is the total intensity image, but we can also look at these polarization ticks that go around the boundary of it that represent the linear polarization direction. So shortly after this work was started, we started a series of discussions led by Ramesh Narayan at the CFA, where we were just looking at a very simple toy model, just a thin ring of emission in the equatorial plane of a black hole. You put some magnetic fields around, you light it up with synchrotron emission, you see how it looks. And the shock was that if we take this incredibly simple ring model that was just meant to be pedagogical, it could actually do a great job of reproducing the polarized structure in this full this full EHT image. Right? We're trying to get away from these very complicated black boxes that require months on a supercomputer and trying to get a spherical cow that maybe gets to the heart of the problem. So with the success of that, we had this team of really talented grad students and undergrads that started generalizing this. That spinned the model, they had more of the Doppler and the magnetic field morphology. And then we can start looking at the different things like the synchrotron emissivity, the redshift, the emission profile, the path length. You can take all these different pieces and put them together to understand what that final image is. And the culmination of this has been a recent paper led by Dominic Cheng that I think is really quite exciting, which just takes a simple dual cone model where you can tune the opening angle of the cone and you can thread it with magnetic fields. And then you can compare that with these GRMHD images. So on the top here are just two GRMHD images. And the next row is showing you the best fit model using this very simple, again, kind of spherical cow model that produces almost perfect representations of that full GRMHD structure. And on the bottom, you can see that it's also not only getting the images right, but it's actually mapping where the emitting material is located near the black hole. So this is why it's called black hole photogrammetry. It's actually inferring the three-dimensional structure of the emitting material. And by the way, it's getting the spin of the black hole correct within 5%. So it's actually doing a great job of trying to get at the black hole parameters while also measuring the parameters of the accreting material. This toy model also involves only 13 parameters. So to put that in context, when we try to do geometric modeling of the EHT images, when we just put, say, a few blobs in the sky or rings, our models require 26 parameters. So it's kind of amazing. By adding more physics into the model, you're able to reduce the dimensionality considerably and lock onto that true structure. So then we can apply this model 7, we can actually get posteriors using EHT data on the black hole parameters of interest, where theta G is the angular gravitational scale, effectively the mass, and A is the spin, and the remainder are the accretion parameters. And something really exciting about this is that the spin is unconstrained. So for most of these toy problems, what you find is that they have false confidence, like finding those false positives in the photon ring earlier. But here, the fact that it's telling you that there are degeneracies between the astrophysics and the physics, and it's telling you that there's not enough information to get at the spin, is really a very exciting step forward to having more capable models that are able to directly measure the black hole parameters from the interferometry. And this is really only scratching the surface of what's possible. So Katie has been leading these really exciting efforts that are trying to do full graphic reconstructions that involve dynamics as well. And this is also work that's being done at the CFA by an extremely talented postdoc, Paul Tita. So I think we're really only opening the door into this whole new range of computational algorithms that'll be able to take this new data and teach us new things about black holes from them. And the last thing I want to emphasize is that by going to space, we also move away from just looking at two sources. So the scaling here is volumetric. If you can improve your resolution by a factor of 10, you can do horizon scale studies of 1,000 times as many black holes. So I think the hope here is that it would be something like LIGO, where for decades, right, LIGO had no detections at all. Then all of a sudden you have booming detection, and then you're seeing a source every month, and now we're seeing a source like here every few days. And LISA will soon see a large fraction of all mergers across the universe. And so with interferometry as well, we can really get on this steep discovery curve where we're able to see, first a few dozen, then hundreds, and then maybe ultimately millions of black holes using this technique where we can read their mass and spin directly off the size of the black hole emitting region and the polarization structure. So for the Black Hole Explorer, this is a sample of the potential targets that we've already found. These are ones that we know that we can study with interferometry that's possible now. The orange guys here are M87 and Sgr A. They're the rock stars, the things where we can see black hole photon rings. But every red source here is another black hole that we think we'd be able to make an image comparable in quality to the current EHT images. Beyond that, there's a whole host of additional AGN and prominent jet sources that we can study. And many of these are extremely interesting in their own right. OJ-287 is the best candidate we have for a binary supermassive black hole. PXS-0506 is the first non-solar neutrino source that also happens to be very bright in the submillimeter. CTA-102 and 3C345 are famous gamma ray sources. So this is really a rich discovery area where we can use space-VLBI to probe scales that just aren't possible with any other method. So in summary, by extending the EH to space, BHEX can give us the sharpest images in the history of astronomy. This would let us to study a black hole's photon ring for the first time. So it's actually locked orbit at the edge of a black hole escaping. It's kind of amazing. I mean, I think the great NASA missions are things like bringing back, rocks from the moon or samples from Mars or going and exploring new things. And here we're bringing back light that has touched the edge of a black hole. And that lets us study spin for the first time and to understand formation pathways for these supermassive black holes. It's leveraging the huge amount of ground infrastructure that's been developed for projects like the EHT, and it's enabled by just stunning new technology like laser communications. So in short, I think the future for interferometry is really bright. A lot of this was born here at Caltech, so it's so fun to be able to come share this with you, and happy to answer any questions. Yeah.
I think that non-GR tests, anything you can say about extensions of GR effects?
Yes, my team never lets me include a slide on this because it's not perceived as serious, but it's actually super cool. So we think that centers of galaxies are Kerr black holes, but we don't know that, and there are lots of alternatives. Some alternatives like boson stars actually don't have photon rings at all. Other things like wormholes have multiple photon rings. So actually wormholes, you'll see nested photon rings of comparable thickness from light on both sides of the wormhole. So it's actually a pretty exciting way to look for non-Kerr alternatives to black holes because it's not like you're looking for some microscopic, it's not this sub% science kind of thing. It's like, is there no photon ring or are there 3 photon rings? And so I think it's a really exciting pathway for looking at exotic alternatives. Yeah. So yeah, I would say definition of the prior is not usually the thing that makes me worry. The thing that makes me worry is that Bayesian analysis is only formally correct when you understand your model space. And in our case, we don't know what the model space is, right? We've done an abstraction of it to some representation, but formally the posteriors could be biased in ways we don't understand because we don't know the real answer. We don't have some ground truth there. But in cases like spin, typically we just use flat priors, or for mass, we might use flat priors that are informed by stellar orbits or something else. Yeah.
Surely we can build this for us maps.
Yeah, it's not easy. So we were originally developing this as a MIDEX, and we started costing the different components for SMEX, and the reason that it might fit within that pretty small box, it's a few things. One is most of the technology's already been developed for other missions, right? We're trying to use lasercom that's been developed on CubeSats, for instance. Yeah, I don't know. I think the game is trying to make this work, but it's definitely a challenge. Yeah, I'm happy to talk more offline about maybe the specifics.
the variability in the image that would be very interesting. Like assuming I would believe in GR, I would fix that. Is there any way you can disentangle that at all? Your R high posterior that comes out from any properties of the local magnetic field structure? In other words, is there any chance we can learn something about plasma physics from this, or is it just?
No, I think you're exactly right. I mean, the initial dream was that you measure the rotation curve, and we know, relativistic Keplerian rotation curves, and maybe you can get its spin from the dynamics. But I think the dynamics here are driven by the astrophysics, and so I think it is a very rich source of information, but something that's very poorly explored right now. And we can use GRMHD maybe as a basis to guide us, but we really have to push harder to understand how to get firm measurements of specific astro parameters from that. For things like R high and the plasma properties, I think spectral dependence, Faraday effects, and the polarization are probably more informative than dynamics, but yeah, who knows? Yeah, there are major challenges. This is a non-traditional sort of paradigm. This is something a lot of people are developing, this concept of a hybrid observatory where it has critical resources in space, but also on the ground. But that is non-standard. The good thing is that interferometry is pretty resilient to, we're very resilient to data dropouts. We're used to telescopes not being able to join for a night. You can lose an entire night of observations for a few sites or for your entire array. And the thing that we're after ultimately is just the time average signal aggregated over a couple of years. So I think that's the only reason that this isn't, catastrophically complex as an operational objective. But it does, it's going to require a lot of coordination, but that's what we do for a living. Yeah. Well, kind of in the middle, actually. So it turns out memory in space is extremely expensive. So one cost saving is that we're not going to have any. So we're not actually going to try to fly a big memory bank. We just want to be recording. We want to pull the data in, digitize it, stream it to Earth immediately. And so it's going to be pointed down, and it has to have an optical downlink active anytime we're actually taking data. But that's a fairly small fraction of the time. Exactly. Yeah. But it doesn't mean you have to have optical terminals around the world so that you can downlink throughout the full orbit. Yes.
Black holes targets for Black Hole Explorer, to get the range for M87 and Sgr A.
Yeah. Well, so you can measure the spin in other ways, but I think they have to be calibrated by something where you're certain that you know the answer. So this is just one example. This is showing kind of the large-scale polarization pattern around a black hole as you're changing the spin. And there's a prediction that this should be fairly sensitive to the spin. But the problem is that we don't have any other measurement of spin, and so this at this point is just a theoretical prediction. But if we could validate this on M87 and Sgr A, where we're able to study the large-scale polarization information and connect that to the spin measured using the photon ring, then there are dozens of sources where we would have the resolution to make this type of measurement of kind of the large-scale polarized structure. So I would say another example would be if you just blur this whole thing out and you just get kind of the size of an unresolved blob of emission, that can tell you pretty accurately what the black hole mass is, even if you don't see a ring or a shadow or the photon ring. So there are ways that we think we could study dozens of sources, but it requires having the sample of one or two that are the gold standard that you're anchoring your measurements to. The limit on the way. So this is the flux density. The limit here is how sensitive your observatory is. And there it turns out that we're running out of ways to make it more sensitive. We're using receivers that are basically quantum noise limited. We're looking at basically perfect coherence. And we're observing at bandwidths that are getting to be a decent fractional bandwidth of your observing frequency. And so at that point, pretty much the only thing you can do is make your dish bigger. And so that's why, yeah, we'd love to fly a 50-meter dish in space, but yeah, the economics and engineering push you to something fairly small, and we're still relying on these extremely sensitive facilities on the ground to get the sensitivity we need.
So let's all thank Michael for a nice talk.